So I'm going to be talking about probabilistic programming with Stan. Let me get my timer on as well. Make sure I do this right. And Bayesian inference with Stan. Given the limitation of the hour time frame, it's going to be a very high level introduction. So I, in fact, started about 7 days before the lockdown. So unfortunately, I haven't had a chance to meet a lot of you in person, but I'm certainly happy to talk about this. My favorite part of this job of working on statistics is working with people doing cool science problems. So if you have something going on, let me know. I would love to collaborate. So now let's see oh, there we go. Okay, so uncertainty of all kinds permeates both science and decision making. And it comes in three basic forms. There's sampling uncertainty. We only collect a finite amount of data, and the data we collect is only a sample of the larger population of data we're interested in. There's measurement uncertainty. The way we actually measure things has noise in it. The scale isn't giving you something perfect. You're measuring galactic mass with gravitationally lensed data. There's all kinds of stuff that gets in between the phenomenon and the measurements that you actually get. And finally, there's modeling uncertainty in the sense that our models aren't all actually correct, right? So we have a model, the model only predicts part of the problem, so there's still uncertainty left over in terms of what the outcome is. So given that it's baseball season right now, I want to quote Bill James, the original sabermetric baseball statistician, who said that the alternative to good statistics isn't no statistics, but it's bad statistics. Now, ironically, Bill James was not a statistician, and arguably his use of statistics were great, but the actual statistics he used were kind of hokey. So don't do what Bill James did, just do what he says. So what are probability and statistics, just from a very high level? Probability theory is about using math to quantify uncertainty. Bayesian statistics in particular applies probability theory to a bunch of problems, both the traditional data analysis problems of statistics, but also the prediction and forecasting problems that you find in machine learning, as well as model evaluation and decision theory. Right, we're in computational centers here. The computational bottleneck for all of this stuff is being able to actually write down the model that you care about in some tractable way, and then actually being able to perform the inference with it, right? So actually just writing it down isn't enough. You need to then be able to do what you need to do with it. I should say, by the way, if people want to jump in and ask questions, you should really feel free. Hopefully there aren't any yet, since it's a super high level overview, right? But let me start with a little philosophy. I cut this out of my job talk, but I think it's really important to talk about this, right? What probability is not? And we're going to start with Laplace, where a lot of good math starts, right? And this is Laplace talking about what's come to be known as Laplace's demon, right? Which is this powerful intellect that knows everything about the state of the universe and everything about low-level physics and can actually just simulate the universe forward and backward. And the important point is that for such an intellect, nothing would be uncertain, right? The idea is that if you actually knew everything, you'd be able to predict everything. Now, this was pre-quantum, and I don't want to get into that kind of stuff, but it's important in thinking about statistics that statistics is really about what we know. And I think John Stuart Mill then summed this up really well about 60, 70 years later. He spent many editions on this book, going through many versions of this, and this is from the 8th edition. So what Mill says is that every event is certain, not probable, right? So this is the same thing that Laplace is saying. If you actually knew what was going on, you'd know what would happen. Right, but what does probability mean then? It's the degree of expectation to which we're warranted in entertaining our present evidence. In other words, it's epistemic. It's about what we know. It's not about events in the world. So this is at least the Bayesian take on statistics. The frequentist take on statistics is another philosophical kettle of fish altogether that assumes probability really kind of is in the world, and I think is a little incoherent in terms of that. But we all work with probabilities in exactly the same way, and I'm not trying to make some big Bayesian frequentist split. You can do a lot of the things you do with Bayesian stats with frequentist stats and vice versa. So let's just consider a simple problem. What's the chance of rain in Edinburgh, right? Just to try to settle some concrete intuitions about what probability means, right? If somebody tells me, is it going to rain in Edinburgh, and they don't tell me what day of the year it is, my answer should probably be 52%. That's the number of days of the year it rains. That will give me a nice calibrated prediction, right? But if somebody tells me it's October, right, then I'm going to up my probability to 55%. It rains a little more in October than it does during the rest of the year, right? So this is just trying to give you the sense that the chance of rain isn't a property of the day. It's a property of how much we know about the prediction problem, right? What if I know that it's not just October, but it's tomorrow, right? But what if I have today's weather report? I actually yesterday went and looked at the chance of rain in Edinburgh, and for today it was 80%, which from my memory seems more accurate than 50-ish. But if it's right now and I see rain, then what's the chance of rain? It's 100%, right? The world hasn't changed, right? This is just my knowledge of the change of what I can condition my estimates of probability on, right? And the point here is that coin flips are exactly the same. If you actually knew exactly like the thumb angle and the force and could do that Laplace style simulation, you'd be able to predict how that coin turned out. It's just, we don't generally know when somebody flips a coin what's going to happen, and 50% is a pretty good estimate that we can actually do some business with, which is kind of the point of statistics, right? We want to get our best guess of what's going to happen, characterized probabilistically based on whatever limited evidence and context we actually have. And statistics and probability, right, which is the basis of statistics, is just all about getting these probabilities right. Right, so let me start with another simple example since it's still baseball season, now 5 minutes into the talk. Let's simulate some data here. I like to do this before starting out a talk just to give people a sense of how noisy binary data is. It's amusing to sit down and watch the playoffs in the World Series in baseball and listen to the announcers get all excited when somebody's had 20 plate appearances or 20 at-bats, right? And they've done poorly. They've gotten no hits. They're like, he's 0 for 10. He's really slumping in the playoffs, just not a clutch player, right? So what I've done here is I've simulated somebody with a 30% chance of success, which is written as a 300 batting average in baseball. And I simulate 10 different at-bats, right? And see what happens, right? And when I did that for 10 at-bats, I get numbers anywhere from 0 to 60% success, right? So it's really super noisy. The thing that I really want to drive home though is look what happens with 100. You think, oh, that's a small sample. We're just looking at 10 or 20 things. Once that person's been up 100 times, we really know something about them. My variation there is still 22% to 33%, right? I'm still not getting a good handle on what their actual ability is, even from 100 observations. Right? You want to be really, really careful with binary data. Binary data is not very informative, especially if you don't have any kind of covariates, any kind of prediction, like are they left-handed or right-handed? How good is the pitcher? You can make this a lot better the same way we could make predicting the weather better by knowing things about the batter and pitcher. The thing is, even when we go to 1,000 observations, our uncertainty is still 29% to 32%. Right? The general trend here is that our uncertainty goes down as 1 over square root of n as n increases. Even with 10,000 at-bats, so 1,000 at-bats is like 2 whole seasons for a player. We go from unremarkable to amazing in this, well, 294 is pretty remarkable anyway. But at 10,000 at-bats, we're still really uncertain on 10 points. So I just want to give you a sense of what the uncertainty is from data, because this is what we're going to be wrestling with in a much larger scale with real data. All right. So let me just now take a little break and go through Bayesian inference and sort of what Bayesian inference is before we dive into doing so. Right, so I'm going to lay down some notation here, and I'm going to have to assume that people actually know probability theory and probability densities, because I won't have time to present all of that, but I do want to fix notation. So we have variables like y that we use for observed data and parameters like theta, which are unknowns that we want to learn about. We want to use statistical inference to observe some data y and learn about some parameters theta, right? We have a joint density function, which is the density of both of those things. And we have a sampling density, which is sometimes called the likelihood when it's a function of theta. That gives us the distribution of our observations given our parameters. When you have a scientific model, that P of y given theta is embedding your scientific process. P theta is your prior or your parameter marginal, which is telling you what you know about the parameters before you've collected data. Right, and then the posterior, the density of theta given y is telling us what we know about the parameters after we've observed the data. And then the marginal on y here is just called the evidence, right? So we're going to uniformly use y and Roman letters for our, well, italic forms of Roman letters for our observations and Greek letters for our parameters. And there's too few capitals and everything in boldface, so we're not bold-facing or anything else. It gets out of hand when you write big models, right? Bold-facing vectors doesn't work when things get complicated, because you get arrays of matrices and things, and you don't, you know, it's like it doesn't go up far enough. So all of Bayesian statistics is driven by Bayes' rule. What Bayes' rule does functionally is it gives you a way of inverting your likelihood model. That is your sampling model that tells you what y's am I going to see given my parameters theta, and it turns it around and lets us compute the parameters, right? So the definition of conditional probabilities first, right? But then we expand that with the notion of the chain rule for probabilities. And then the trick is a lot of people stop here with Bayes' rule, but Bayes' rule keeps going. We actually express y as using the rule of total probability as an integral. So we marginalize out the theta, and then we do the inversion again. So we're finally left with this form here. And that form fully expresses our posterior in terms of our likelihood and our prior, right? But normally we don't care about that downstairs integral, which is really hard to implement. And we know that up to a proportion, the posterior is proportional to the likelihood times the prior. And that proportional constant doesn't actually depend on theta, right? It's just the evidence for y, right? So this is the very simple algebra and probability theory that's driving everything. And what's neat is Bayes set this up, but he couldn't actually solve the integrals that resulted for doing anything interesting. So let's look at what those look like. In Bayesian stats, we have parameter estimation. So the typical way we estimate parameters in Bayes is we take the posterior expectation conditioned on our data, right? What this gives us is the posterior average, right? And that has the property of minimizing expected square error. So it has a nice probabilistic interpretation in terms of expectation. So if we look at the error, the expected error, the difference between the squared difference between theta and the true values, using this form of parameter estimation minimizes the square error. Again, all conditioned on you having the right model, right? But this isn't a probability. That's just giving us a single number, right? What's in statistics, we're generally concerned with event probabilities, right? We have some subset of the sample space, some subset of the parameters, and we want to know what's the probability of that event. Is it going to rain tomorrow, given everything we know? Is this team going to win the World Series, given everything we know, right? And that can be phrased as the expectation of an indicator function, right? That indicator function is just, is that theta some subset is in the set capital A, right? So we can always phrase event probabilities as expectation of indicator functions, right? So the point here is that all of our computation is going to look like an expectation. It's going to look like an integral over the posterior. This form here plus that integral means you're just averaging whatever this expectation value is here over the posterior parameters. So we do predictive inference the same way. So this is posterior predictive inference. We're going to get new data y tilde, and we want to predict new data given the data that we've already seen. This is just going to be the expectation of the likelihood function here, which again is just going to be a fairly simple integral, right? So it gives us a way of characterizing the probability of new inference. And what's characteristic of Bayes is we're integrating over our uncertainty. We're averaging our uncertainty out, right? So what would happen in a frequentist setting is we'd take a maximum likelihood estimate for the parameter estimate. We find the theta that maximizes the density of theta given y, rather than doing this kind of averaging. This averaging tends to be more robust and works better when you have probabilistic scoring rules, but that's a different talk. So the way something like Stan works, and what Eric's going to tell you a bit more about, I think, in the next talk, is through Markov chain Monte Carlo. So what Stan's going to do, and basically what pretty much every kind of computation for Bayesian inference these days does, there's some edge case exceptions, is we take some kind of sample. We have some kind of mechanism that lets us express our model, and then we can sample from the posterior. We get this theta 1 through theta capital M, draws from the posterior, and then we can calculate expectations just by plugging those in. This slide is why this stuff all works and is practical and is actually easy for somebody to use, right? If you want to calculate one of these complicated expectations, like we had on the previous slide, all you need to do is you need to average over the function that you're trying to take the expectation of over the posterior draws. And what we know is from the central limit theorem, or from the Markov chain Monte Carlo central limit theorem, is that the error of this approximation goes down as 1 over square root of m, or in the MCMC case, of 1 over square root of the effective sample size. When you're doing Markov chain Monte Carlo, you have correlation between your draws, so they're not going to be completely independent. So how does this play into decision theory, right? Well, an agent is typically going to have a choice of actions. They might be discrete, like do I go to college, or continuous, like how much money do I invest? And there's going to be some kind of utility function, which is going to be based on the state of the world theta, all these parameters, right? It's going to have risk aversion. Everything's going to be rolled into this utility function. And then in Bayesian decision theory, we look at the expected utility conditioned on Y, and we want to optimize that, right? We somehow want to choose parameter values, and we want to choose an action A, right? Sorry, not parameter values. We want to choose an action A that maximizes that utility, right? So, and the point estimates that we would typically get aren't plug and play because there's nonlinearity, but this kind of expected utility through Bayes, it will give you the right answer, right? Again, this is all conditioned on your model being correct, right? Which is something I really want to talk about more, but I'm not going to really get a chance to in this talk. So optimal decisions are just going to be maximizing that utility. Sorry, that should be an argmax here. That should be an A, not a theta, right? And we can compute this expectation via MCMC, and then we can automatically differentiate it, right? So if you have some utility function and you're looking for some kind of action, we can do this all with Bayesian decision theory this way, right? Popular applications of that are things like online A/B testing. We have some discrete choice of action at every time point. We get some reward at every time point. This is called like a multi-arm bandit problem in the old stats literature and in the modern machine learning literature. In current stats, it's just online test design, right? You're just doing some kind of trial design. It's a standard sort of part of stats, so it doesn't get a special sort of name. The point of this is you want to do some kind of explore and exploit. You want to take your next action, chosen with probability of something like proportional to that action being the best. This is a strategy called Thompson sampling. So one of the projects I'm working on now with some people from Yale and Michigan is looking at COVID antibody testing and virus testing, and how we can maximize the explore and exploit parts of this to, if there's a vaccine, get it out to the right people to minimize population and number of population infections, right? So this all fits into this kind of framework. Right, but what are we going to do with our Bayesian workflow? Right, we've got some kind of problem. We're going to design some kind of experiment and collect data, which is its own really complicated workflow. And then we're going to consider gradually increasing model complexity, and we're going to test the model and the software on simulated data. Right, we use a technique here called simulation-based calibration that makes sure our algorithms are correct. And actually, if you simulate from the prior, get the right answer. Then we're going to perform prior predictive checks and make sure that the prior information that we're adding is actually sensible. Then we're going to fit the model to some real data, right? And then we're going to form posterior predictive checks and say, does that model that we fit to the data actually fit the data and capture parts of the data that we care about? And then we're going to perform held out checks and cross-validation and say, does it predict well on new data that wasn't part of our training set? And we go through these typical steps. Often, classical statistics stops before the final step, right? And also doesn't allow this kind of software type waterfall going back to the data, refining it. So in some sense, Bayesian statistics looks a lot more, in the way it's actually practiced pragmatically, looks a lot more like machine learning than the sort of classical statistics does. So let me go through an example. This is an example of the birth ratio that was done by Laplace. It was actually the first real application of Bayesian statistics, and it's about the simplest kind of application, but it will show you the mechanisms in practice, right? So Laplace did this in 1781, All right, so he's working there by quill and candlelight, figuring all this stuff out. And he had data because Paris was collecting a lot of data. So between, these 25 years, there were, 250,000 boy baby born and 493,000 girl babies born. So we're going to assume the sampling distribution is binomial. That is, there's just a probability theta that a boy is born, and each birth is assumed to be independent. Oh, right. Sorry. My wife's correcting me from the other room. The N there is the number of total births, not the number of female births. So the female is the difference here, right? So the sampling distribution is binomial. You're assuming each birth's independent given the probability of success. Our prior, we could use a more informative prior here. We have a pretty good idea that the number of births close to 50%. Laplace just took it to be uniform. Assume we're completely ignorant about male versus female birth ratio. This could be parts on an assembly line failing. It could be clinical trials. We're just completely ignorant. Somebody, like machine learning people, somebody shoveled a hopper full of data on us, and we throw it into the bin and see what happens here, right? So the posterior, right? This is what Laplace was able to work out. So Bayes set this problem up, but he wasn't able to turn the crank and actually solve the integral that you get here, right? Whereas Laplace just, again, by candlelight, somehow managed to turn that crank and use Euler's beta distribution, beta function to normalize everything. And anyway, what you get is you get the answer. I'm just going to give you the answer up front. The probability is 99% that the birth rate is somewhere between 0.508 and 0.512. This is the male birth ratio, right? But the probability that theta is greater than 0.5 is a really close to one number. It's 1 minus 10 to the minus 42. We can't solve that second thing with MCMC, right? But we know this is a simple enough problem. We can solve it analytically like Laplace did. And Laplace concluded that he was morally certain that more boys were being born than girls. And this is held up under modern analysis. It turns out that it's like 51 to 49 in terms of boys versus girl births. So how do we code that up in Stan, right? And here's a Stan program. So Stan sets a program up by laying out the data and then laying out the parameters and then laying out the model, sort of just how I set it up theoretically. When I was designing the Stan language, and my own rule with respect to Stan, I wouldn't necessarily say I'm the lead developer now. I wrote the prototype and I designed the language, and I wrote the first version of the language, and I wrote the first version of our differentiable math library. Now Stan is huge and there's a lot of programmers on it. It's not just me. But when I was defining the language, what I wanted to do differently than things that had come before it, like bugs and jags and ADMB, is I wanted a model in Stan to be very readable, even by people who wouldn't necessarily be programmers in something like this. So it's not embedded in Python, it's not embedded in R, it's just a very simple C-like programming language. It's hopefully readable to people. And I laid it out exactly the way you lay out a probabilistic model when you're computing with it. So you specify the data, the parameters, the model, and then you can have some transform quantities. So the data is just the way we wrote it. The parameters bounded between 0 and 1. Stan needs to know transforms on parameters because it transforms everything to unconstrained support so that sampling and optimization are easier. And then the model's just that binomial model. The implicit uniform prior doesn't actually need to be stated. I could say theta has a uniform 0-1 distribution, but it wouldn't do anything computationally. It doesn't add anything to the log density. And then we have some generated quantities that are going to let us compute these integrals here, the ones that are involved in this, right? And that's going to be characterized as an indicator function, right? Theta greater than half. We just code that as an indicator function, define a variable theta greater than half in the obvious way. We define it's going to be 1 if theta is greater than a half and 0 if it's not. And then we're going to define a simulated result where we're going to take a binomial RNG and simulate 100 draws from theta just to see what's going to happen. So when we run this, we take the program Laplace.stan, we fit it, we tell you what the posterior intervals are, and this is going to give us our posterior 99% interval on theta, which is that 5.08. 50.8% to 51.2%. Theta greater than half is going to round off to 1.00, right? We can't even represent 1 minus 10 to the minus 42 in double precision floating point. And the simulated value is 50.9. So this is saying, what would happen if, what do we expect to happen in the next 100 births, right? Well, we expect somewhere between 38 and 64 male births, right? That's the best we can do. We have a very tight estimate on theta, but that doesn't lead to a very tight estimate on what the next 100 births are going to be, right? So we know what they're going to look like on average, but remember, binary data is tricky. Any given sample of 100 isn't necessarily going to look like that. Right? So this probability theta greater than 0.5 is just estimated using the MCMC technique for expectations. It's just the sample mean of that indicator function. It's the number of draws that actually satisfied that is an unbiased estimator of the probability. Right? And Y sims the forecast, as I said. So one of the things I want to talk about with respect to statistics here is calibration, because what we generally want to do with Bayesian statistics and statistics in general is we want to make probabilistic predictions, right? We want to make predictions like there's a 60% chance of rain tomorrow, or the value of the S&P 500 at the end of the year is going to be somewhere between 3,200 and 3,400 with 90% chance. Those are the kind of predictions we want to make, probabilistic kinds of predictions, right? And what does it mean for a probabilistic prediction to be calibrated, right? Well, this is actually not something that a traditional Bayesian would do. This is a frequentist evaluation of probabilistic forecasts, right? So a traditional, very subjective Bayesian who thinks that everything's about me and my knowledge and everything else and my beliefs, right, would just say you build your model, you plug things in, and your posterior is what your posterior is. That's what you're stuck with because you expressed your prior, you expressed your model, and then you turn the crank. Right, in reality, this is a back and forth between the data, how much data do we have, how much model can we fit, and we bounce back and forth. And what we're aiming for is to get calibrated predictions to start. That's a baseline. We want our predictions to be reasonably calibrated. What does that mean? It means that on 75%, if we forecast a 75% chance of rain, then we want roughly 75% of those days to be rainy, right? The way to express this probabilistically is we can make a hypothesis test. For n-calibrated predictions of probability theta, right, we expect the distribution of days that it rains to be binomial in theta. So if we look at 100 days with 75% right rain, we expect a number, probably between 70 and 80 days of rain out of 100, or maybe 65 and 85, because binomial is tricky, right? But what does it mean to be a calibrated prediction? Let's go back to our example in Edinburgh. If I just make a constant baseline prediction of 52%, right, that's going to be calibrated if I evaluate over random days of the year, because that's the number that actually works. On the other hand, if I know what month, if somebody tells me for each of those days what month it is, then I can use the average number of rainy days for that month, and my result's still going to be calibrated, evaluated over exactly the same data set of days. But what's going to happen is it's going to give me sharper predictions. I'm going to be able to say 65% chance of rain in December and maybe, 45% chance of rain in July, right? Instead of just 52% everywhere. So adding more information lets us make sharper predictions. Is weather.com's forecast calibrated for tomorrow? I don't know. That's an empirical question. We'd have to go evaluate it, which is one of the things we do when we build these predictive systems. We want to do ongoing, we field these things. We want to make ongoing measurements of whether our forecasts are actually calibrated. But calibration isn't enough, right? We want calibrated predictions that are also sharp, right? In some ways, that 52% prediction is a much worse prediction than a 65% prediction. 65% gives us more information. In what sense does it give us more information? It has lower entropy in the differential entropy sense, right? So narrowly concentrated predictions are sharper. If I say there's a 90% chance that a value is between 58 and 59%, that's a sharper prediction than if I say there's a 90% chance it's between 50 and 60%. Given calibration, we prefer a sharper prediction. Probabilistic predictions near 0 or 1 are sharper, right? So a probabilistic prediction of 95% is sharper than a probabilistic prediction of 60%, right? So in general, we want our probabilistic predictions to be near 0 or 1, given that they're calibrated. The problem that I think people are finding in machine learning now with these deep neural network models is that the models aren't actually very well specified for the data. There's too many degrees of freedom in the models, and there's too much modality in the fitting. And what winds up happening is most of the predictions, and you build a big, sort of prediction that's giving you, a 20,000 vector over breeds of cats or something, or types of animals, or, something like that, or natural language translations, right? And what's going to happen there in most of the machine learning applications is that your predictions are not going to be calibrated. They're going to be super attenuated, and your predictions are going to look like 99.99% and 0.001%, right? And in reality, you're going to be right like 95% of the time, right? So what people do in machine learning nowadays, until we can sort out like how to actually calibrate neural networks, is people will run something like a logistic regression, like a traditional statistics method, over something like a neural net to calibrate it. Interestingly, my very first stats paper in the mid-90s actually used this technique on something like Word2Vec. I used to do natural language processing of building something that had a really attenuated prediction and then fixing it with logistic regression. So these techniques have been around for a while. How do we evaluate our inferences? So we've got a model, we've got some data, we fit the model to the data, we want to know if it's right. Well, generally what we want to do is we want to maximize sharpness subject to calibration, right? So the goal is to have consistent, useful inference from finite data. So for instance, this is going to be similar to minimizing variance subject to zero bias for estimators, right? A huge amount of the frequent to stats literature, like if you go into what people actually do in econometrics, they don't do economics. They prove that some estimator has zero bias in the long run, right? Because this is like what people cared about in frequent to stats. We care more about having calibrated probabilistic predictions. The frequentists in doing hypothesis tests cared about calibration, but they cared about calibration for estimator uncertainty. It's slightly and subtly different in a way that really needs a whole lecture that I won't be able to get into. So Bayesian models are by definition calibrated if they are well specified. And what I mean by well specified is they capture the true data generating process. The problem is, though, that models are always approximate, right? As I think Bach said, all models are wrong, but some are useful. It's sort of like quoting Alice in Wonderland, so I didn't want to actually write it into my talk. It's so overused. But we need to test and fit to real data and real predictions, right? To actually see if things are well specified. We're going to take exactly the machine learning methodology, use held out data, cross validation. We're going to enter Kaggle contests. We're going to set our system up at some business that cares about the answers and see what happens. So let's go through a second example. I should stop there and see if there's questions as we go along. I really am happy to take questions as we go. If not, I'm going to dive into a second example here, because otherwise I'll just talk in one long paragraph, really one long book. Okay, nobody's got anything now. We're going to go back a little later than the 1780s, way back to 1926. Oh, was somebody there?
Yes, hello.
Yes.
Yes, no, that's very interesting. Thank you very much. I wanted to ask, how fast is it compared to the other Python packages there? Like how this language is really fast to do the MC analysis?
Oh, how fast is Stan?
Yes.
Yeah, I've got some more on that on some later slides, but the basic idea is like if you compare against things like PyTorch and TensorFlow, Stan's about an order of magnitude and a half faster on the CPU, and we have a vastly more expressive language. We're about an order of magnitude slower on the GPU, right? So if you're doing something that has a lot of SIMD calculations, a lot of big matrix operations, and you really want to precompile it and go fast, you're better off using something like TensorFlow. If you have a statistical model that looks like the one I'm about to show you, Stan blows away the competition in terms of speed.
Okay.
Right. Mainly that's not because we have better engineers than they do. Arguably, they have a lot better engineers than we do on their project. It's that they've been focused much more on approximate inference methods for neural networks. So if you go talk to the people building PyTorch, building TensorFlow probability, building JAX, all of those people are focused on building big neural networks, which has the property that most of the computation is big matrix multiplies. Big matrix multiplies are like made for the GPU. So they've optimized that particular path, whereas we focused on building something that kind of works on desktop and notebook computers and runs fast. Having said that, you can parallelize Stan and throw some Stan computations on the GPU. It's just we haven't engineered that as well as. So you can get like an order of magnitude speed up or even more using GPU, using multi-core with Stan, but we haven't engineered that as well as TensorFlow or PyTorch.
And does it work with OpenMP or MPI?
That's a complicated question.
Okay.
We have MPI running for multi-core, either within a single box or across boxes. We're not using a lot of OpenMP. We're using TensorFlow thread library, the TensorFlow building blocks, TBB, to actually build the low-level stuff. We're probably going to switch over to the C++ threading, though, longer term, rather than go with OpenMP. There's some OpenMP stuff in there. It's a mess once you get down into the engineering details of this stuff. It's another whole.
So it's just my question is the last one. It should be possible to link a Stan to any simulation code that we have. So if I have any code that generates data.
No. Stan, you need to actually write, if you can do that in C++ and provide derivatives, yes, you can do that, right, with some engineering, but otherwise you need to write your model in Stan. Right. This is the same thing for like TensorFlow, the same thing for PyTorch. You need to use their libraries. You need to use the TensorFlow, right? They pun NumPy, but in fact, you need to use the TensorFlow library to express things. If it's not expressed in TensorFlow and it's expressed somewhere else in Python, you need to code it over to TensorFlow.
But if you have already code written in C, you cannot just link it directly to them, like in kind of a loop?
C, no, it needs to be templated C++. If you have templated C++ and it bottoms out in standard math apps, then yes, you can use it.
Okay, sounds
right?
good.
But standard C, no, you need derivatives because everything we do, every modern computation requires derivatives.
Thank you.
Right? Yeah, if you don't have derivatives, it's not going fast. So let's look at another example of Stan here for population dynamics from Volterra, 1926. This is populations of prey and predator species, and the data we're going to fit is lynxes and hares. So Volterra built a mechanistic differential equation model, just a simple ODE, and if you look at it, it's kind of a harmonic oscillator kind of setup, where alpha is the prey growth rate, beta is the predation shrinkage rate. So as the predator population goes up, the prey population goes down, and vice versa, right? Gamma is the predator shrinkage and delta is the predation growth, right? So if you put all that together, it gives you a very simple model of continuous population dynamics, which is obviously an abstraction, right? These are discrete animals breeding. It's not some continuous, these numbers are integers, U and V, but we can model them continuously. So this is what the analytic solution looks like. And I actually pulled this out of Volterra's 1926 paper for a couple different sets of parameters. The axes there are the populations of predators and prey, and the orbits are, if they're stable, what's going to happen is time goes around those circles. So the prey, so if you look at the population of, I don't know which axis is which, unfortunately. It's going to go up from here to a low of here and vice versa going across this way. So we can look at this in some real examples coming up. So U and V are observed. This is the population sizes at a given point, and U hat and V hat are actually predicted by the mechanistic model, right? And what's going to happen is we're going to assume that we're going to have independent error proportion to the population size. So the idea is that we're going to solve these differential equations. Once we have our parameters, alpha, beta, gamma, and delta, and we know what the population is now, we can run these equations forward and solve them for some point in the future. We're going to assume that we have some measurement error, which is proportional to the population size instead of additive. That makes it log normal instead of normal. So if you have errors that are proportional, if you have a positive value and errors that are proportional, you want to use something like a log normal distribution. We're going to use fairly weakly informative priors here. These priors are simply going to determine the scale of these computations, right? Because beta and delta are product terms here. So you wind up getting beta times u here, right? And which is why these are on a smaller scale. So here's what the data is that we have. This is from Hewitt 1921. They looked at the Hudson Bay Trading Company in Canada and recorded the number of lynx pelts, which is up here on the top. The number of rabbit pelts. These are snowshoe hares actually, and the number of lynx pelts that were caught by trappers. It turns out lynxes eat pretty much exclusively snowshoe hares. Right, so this is a pretty tightly controlled population. There's also some wolverines, but that's a minor population. This problem gets hard when you get 3 species in terms of the chaos of the ODE. Right, so let's look at what the data looks like plotted. This is just the data we've got here plotted in a way that'll be a little easier to see. Right, so on the left we've got the lynx and the hare populations, and you can see that they're both cycling. Right, but they're offset in terms of the cycles, right? And when we plot them over time on the right-hand side with the hares on the vertical axis and the lynx on the horizontal axis, we again see the population cycling like this. Right? So the pelt data is really just a proxy for the population. What we're really predicting here is how many pelts are going to be collected. We're just assuming that this is proportional to the population somehow, but we don't actually know that. We'd need to tie this together with something like a Mark recapture model if we wanted to actually estimate the total number of the populations. This is really just estimating the number of pelts. And you've always got to be careful about that in statistics because you often only have proxy data, which means you're predicting proxies in the future, right? What does this look like in Stan, right? Well, we just code up the differential equation. Right, this right here, theta is going to be the parameters of the differential equation. I probably should have rewritten this slide because in our very latest release, we just introduced a much simpler way to write all these differential equations down. But in this version, you're packing up all the parameters and all the data as vectors and sending them in. And this is just giving you the first derivative, and this is giving you the derivative of the second component. Right, and then Stan has an ODE integrator, right, where we basically just throw in the system, right? So Stan allows functions as arguments to other functions. And this is the way a function's defined in Stan. It returns a real array. And then we have our noise model, which is just going to be log normal. So these Z's are going to be the predictions, right? Given our actual parameters, which are packed up into this parameter vector theta, Z is going to be what our model predicts. And then our observations are going to be what our model predicts plus noise. Right. So, and this is what the fit looks like from Stan, right? So what we've got is we've got the measurements that we actually took are the red dots. And what I'm plotting here, I think are 90% posterior intervals. Maybe I should have written which I was plotting. But anyway, this model is fairly well calibrated. So if you look into the future, so over here, it's predicting future hare populations and future lynx populations. Like a lot of statistics, we would not expect this to go infinitely far into the future. All kinds of things might happen. They might completely destroy that environment. And there might not be any hares or lynxes 100 years from now. Who knows, right? There may be a rebirth and they maybe go way up. So our predictions and stats are typically going to be limited to when the underlying conditions haven't changed, right? So you see these predictions going out into the future are looking very uniform. You wouldn't want to trust this 100 years out, so you have to be careful. But in data, it's very well calibrated. And then what we'd want to do is keep collecting data over time, or we'd want to do things like fit with half of our data and see if we could predict going forward. Right, and here's what 100 predictive draws of the population looks like. So this is just like if we draw parameters from our posterior, this is like 100 possible paths, and they're discrete simulations over time here. So that's what they would look like. So often this is helpful for plotting, right? So how does this work? This is very similar to a lot of models. It's the same kind of model we use for pharmacodynamics. It's the same model we use for soil carbon respiration, where we take into account leaves producing biomass and enzymes breaking those down into carbon, and then that carbon getting sequestered and getting released. It's all just a dynamics model that looks like a differential equation, right? And that differential equation model predicts our expected behavior based on our parameters. And then we add some kind of error model because our model's not perfect, right? There's a lot going on in these populations like weather that we haven't taken into account. That all gets shoveled into our noise model, right? And we can look at our answers and say, hey, right, our answers are really bad because, oh, there was weather. And this year, things were way down because it was freezing cold for an extra 2 months and a lot of the populations died. That's how we make our models better. We see that our models have residual error, and then we're like, oh, can we go get the weather data? Can we add predictors for weather into these equations and so forth, right? This is how our models get better over time, right? But then we just turn the Bayesian crank here. We added some weakly informative priors, we turn the Bayesian crank, and then we can sample from the posterior. And this works for a lot of scientific models that can be expressed as dynamics, or even ones that can be expressed much more simply. So another application of this kind of model is the
Bob,
SIR model.
Could I ask you a question?
Sure.
So I work generally in astrophysics and galaxy dynamics. We use a lot of ODEs, but we're often in a regime where we have observations of some phase space coordinates, but we may not know the times or the phases. So this is maybe too technical, but last time I looked, the stand couldn't handle unknown times. Like you couldn't take derivatives with respect to the times. Do you know if that is implemented now?
Oh, I don't think that got added. People have been thinking about it, but I think the answer is still no.
Got it. Okay.
There's a lot to do. If people want to jump into the project, we're always looking for new developers. So it's the kind of thing that if you can work this out and code in C++, we love to get new contributions.
Cool. Thanks.
I think the answer is still no. So let me just give you a rundown of like some linear models and what they look like in STAN, right? So here's what a logistic regression looks like. Right, we got a bunch of observations that are binary. We have some regression coefficients. We put a normal prior on those, and then we have a Bernoulli observation, right, that's taken on the logit scale, right? So STAN lets you express these things fairly compactly, right? K is the number of dimensions, N is the number of observations, X is the data matrix, Y is the list of observations, right? So this is all quite simple. Right, here's a linear regression where we want to make predictions, right? So this is just a simple linear regression, right? This is what a linear regression looks like probabilistically. We have a linear predictor and then some normal noise around it, right? But then we can do these generated predictions for new data, right? We can look at predictions for Y tilde given new predictors X tilde, and this is how we actually do prediction, right? And you can run this in 2 stages in STAN as well. We can have something like time series model, right? These are popular in finance for a lot of dynamics where we have some vector that's growing over time and the value at time step n+1 is equal to the value of the time at time step n plus some noise and some innovation. And we have slicing and everything else like that. We can have priors that actually have covariance, right? We have a really cool prior proportional to the determinant, which lets us concentrate priors for covariance matrices around unit correlation, right? So this is something where we're doing a random effects model, and we might have something like two different random effects for a person that are going to be correlated. So for instance, in COVID seroprevalence, right, we're going to have a sensitivity and a specificity for tests at a given site, and those are going to be correlated because test sites are either going to be sloppy or they're going to be good, and both their sensitivity and specificity are going to go up and down together. So, and we can go all the way out and build things like Gaussian processes. We just define our covariance matrices down here, and then we do prediction this way, and we have multi-normal, multivariate normal sampling here. It's all fairly efficient. We're working on making this a lot more efficient going forward. So let me just give you a brief overview of Stan before wrapping up here, right? So what is Stan? It's a domain-specific probabilistic programming language. So what a Stan program does is it really defines a probability model that's differentiable with respect to the parameters. So we declare the data and the parameter variables, and then Stan defines a differentiable log posterior function, right, over the parameters. And under the hood, it makes sure to take all of our constrained parameters. Like if we have a parameter that's a covariance matrix, it actually uses the Cholesky factor of that covariance matrix with positive diagonals as the actual basis for computation, because that's unconstrained, right? The log diagonal and the off diagonal entries in a Cholesky factor, completely unconstrained, put it back together, get a covariance matrix, right? And then it defines predictive quantities, all right? So Stan inference, I haven't talked a lot about this, but we use MCMC for full Bayesian inference, and we use variational and Laplace for approximate Bayes. So there's a lot of models get so big that you really can't turn the MCMC crank really easily. But then it gets hard because then you have to make sure that your approximation isn't introducing a lot of damage. So availability and usage, we pretty much run on every platform and in sort of all the standard languages. So we can embed in R, Python, Julia, whatever. We have well over 40 developers, which at this point is over 15 full-time equivalents. We have a lot of people who are sort of working away full-time funded on this. The users, I would say, is probably over the hundreds of thousands, but it's very hard to measure. It's not, you know, if you count everybody who ever used it in the class, you get one number. If you talk about people who used it this month, you get another number. But there's hundreds or thousands of companies using this. We get millions of downloads for all of our releases, but who knows what that's measuring. We have about 3,000 registered users on our mailing list, and we get around 6,000 non-bot views and probably around 100 or more messages a day on the message board. So it's really hard to keep track of. There's 10 books that have been written based all or partly on Stan. There's well over 100 courses that use Stan, including at least about a dozen that have full courses with notes and exercise and everything on YouTube. I think the articles using is over 6,000 now. The slide's a year old. And we had our 5th conference. So we've had well over 1,000 people. We had like 250 people attend our virtual StanCon earlier this year. So it's a very vibrant and active community. In fact, the only reason this works is because the community is very active. Like people ask me why Stan's successful. It's because we're really good to our users and helping them get done what they need to get done. And it's the community. So the people generally in applied statistics, when they want to do something, they go and look and see what other people have done, right? Once you have this volume, right, people can go to a search for a Stan model for just about any kind of common statistics now that's at least within Stan's expressive scope. So I cannot stress enough that if you're building your own software, pay attention to the doc and pay attention to having a good users group and actually helping your users, because those users you help in the first couple of years of the project are the ones who are going to be helping the other users in the 5th and 6th year of your project, right? So applications of Stan have been in just about everything. I'm not going to read this out. I always have a hard time writing this list out, right? But it's pretty much everything at this point that you can imagine. Industries using Stan, there's tons of use in industry. I went to a meeting in Ann Arbor and somebody from Domino's Pizza said they'd actually picked up Google's model for marketing attribution. So Google uses Stan to measure how much of an impact Google ads have versus, say, TV buy. And Domino's found Google's model online that they published and said it worked great for us. Legendary Entertainment, which is a big Hollywood marketing production company, also is a big Stan user. Demand forecasting, Facebook, Salesforce, other companies use Stan time series models to predict utilization of resources. There's tons of financial and econometric modeling, including 2 of the big hedge funds in New York, 2 Sigma 0.72, which I know about because Stan people are working as consultants for them. Pharmacology and clinical trials were pretty much all over that. Pretty much all 4 teams that were left in the playoffs were all Stan users this year, including the Tampa Bay Rays. Go Rays. We like the Rays because they have a low budget and high analytics. So whenever Tampa Bay wins in baseball, it's a big win for analytics. Survey sampling, YouGov, who's doing about the best polling now, is using STAN, Doug Rivers. Agronomy, computational stuff for climate, real estate pricing, industrial process control, pretty much anything you can name. Again, we're everywhere. Why is STAN so popular? So I expressed this already. It's the community. It's a large, friendly, helpful community. We have good documentation that starts from novice to expert level. It's very robust. We've really emphasized building industrial strength testing and diagnostics over just adding new features. This is very hard to enforce, right? People come into a project, they want to add new features. When other people come into your project, what you want them to do is fix things and test things. So there's a bit of a tension there in running a big open source project. It's very flexible in that we have a highly expressive language and a large math library. It's very portable by OS, language, cloud support. It's very extensible and developer friendly. There's hundreds of packages that have been written on top of STAN to support particular models like education models or clinical trial models or things like that. The speed is, compared to things that came before it or things that still exist, on the order of 2 to infinitely faster, because a lot of things can't even compute the models, right? Scalability compared to stuff that came before was about a couple orders of magnitude. That was mainly because those things were very poorly engineered. We could have made the things that come before and did Gibbs sampling scale. It's also very open. We went with a BSD license to make everything permissive and open. That was actually a struggle with academics who largely wanted to go with GPL because they didn't want industry people stealing their stuff. So let me just do a brief overview of how STAN actually works before wrapping up here in a couple minutes. So we use a technique for sampling called Hamiltonian Monte Carlo, where we treat the negative log posterior as a potential energy. And then we impart a standard normal kinetic energy each iteration of MCMC. And then we just simulate the Hamiltonian dynamics and roughly take a draw from within that dynamics, right? This has geometric ergodicity, which is what's required for the MCMC central limit theorem for a much wider ranges of model and data situations than other systems, but it requires derivatives, right? And the problem with Hamiltonian Monte Carlo is it's very, very sensitive to tuning parameters. It's sort of like stochastic gradient descent. Works great when you get the learning schedule right. Otherwise, it doesn't do anything and just runs off into space. What we did, and Matt Hoffman did this in the no U-turn sampler, was figured out how to adapt the leapfrog algorithm during warm-up for a Euclidean metric that's estimated with sample covariance, either diagonal or dense, depending on the size and how much correlation there is in the posterior. And then we adapt the leapfrog algorithm during sampling as well. We simulate forward and backward in time until the dynamics start coming back to each other, because basically we want to evaluate the level set of a given Hamiltonian value, right? And then we do a multinomial sampling there. This algorithm, the no U-turn sampling, Matt Hoffman and I were hired by Andrew Gelman not to work on STAN, but to speed up hierarchical models. We couldn't figure out how to do that, so instead we worked on a much more general problem, which had that as a byproduct, as is often the case, but we couldn't figure out how to just solve the hierarchical model problems. And Matt mainly worked on the sampler, and I worked on the language and the math library. Here's an example, though, from Matt's paper with Andrew. This is 2 dimensions from what should be a fairly simple thing to sample. It's about a 90% correlation on a 250 dimensional normal. This is a very easy posterior in some sense. Like the Hessian does not vary, so the condition stays the same everywhere over the posterior. These Metropolis and Gibbs represent 1,000,000 draws thinned down to 1,000 draws. And these were optimally tuned Metropolis and Gibbs too, right? This is not like we were doing a bad job on Metropolis and Gibbs, because our first inclination was to just build a faster Gibbs sampler. And we realized from these plots that this just wasn't going to work, right? This, on the other hand, is 1,000 draws from nuts and 1,000 draws from independent sampler. This is the computational reason why people use STAN. Right, it's really the computational reason why people use the no U-turn sampler, because a lot of other projects like TensorFlow Probability, PyMC, Turing.jl, and Julia, a lot of the other systems are also using HMC. Then we have reverse mode auto diff, which when we did this 10 years ago, there was not a good extensible system for this. There was a lot of really badly engineered C++ code, so we built our own. If we were doing this now, we'd almost certainly use PyTorch or TensorFlow or something and jump onto that project. Stan's auto diff compared to the other C++ auto diff is, again, depending on the scale of the problem, this is the baseline for Stan along 1, and this is how much slower these other systems are. And the one on the bottom is just computing in doubles. Right, so we did a paper on this. So this was a lot of careful engineering, unfolding the assembly language code that was produced, that kind of stuff. We also have forward mode auto diff, which I just finished off last year, all the testing for, although an undergrad actually built most of it. And the higher order auto diff, I don't really want to go into that, but I do want to talk a bit about shortcomings before wrapping up. So where does Stan fail? When you have extremely varying posterior curvature, when the Hessian, the condition changes there, and it also runs into floating point problems. So log CDS, log CCDS, gradients, all that stuff is overflow, underflow problems. And scalability with respect to data and parameters is okay, but we'd really like to do a lot better than that. Missing features, we don't allow something like black box log densities, which somebody was asking about before. If you want to do something like that, my recommendation is to use something like MC and Python. We don't have checkpointed auto diff for things like large Gaussian processes, which we need to build. We don't do filtering. We don't do something like sequential Monte Carlo, so we don't have a way to do online model updating. I'm not sure that stuff actually works, but we don't have that. We also are working on more stochastic algebraic and differential equations and PDEs and more structured data types like ragged arrays, sparse matrices, and closures. The other thing we don't do is discrete parameters. Instead, we focus on tractably marginalizing things. We do like mixtures and HMMs this way. It's efficient in theory, but it's actually difficult for a lot of our users. You can usually look those up from the EM and max marginal likelihood literature from the 80s, but otherwise, this is a big bottleneck for a lot of our users. The thing is, though, you really need to do this. Discrete sampling doesn't really work. So you want to do this even if you have a system that can do discrete sampling. And then I have some pre-canned answers, but rather than that, I think I'll stop here and let you guys ask questions before I just jump into a bunch of canned answers.